So in this section, we're not actually going to be dealing with any new methods of solving counting problems. Now we're going to be using the methods that we know and have learned to solve some more complex problems with them. So, first example, we have 5 swimmers in the first heat of the race: Aubrey, Betty, Cam, Deanna, Elena. In how many ways can the swimmers finish first, second, and third? So the key thing here is we're actually talking about the placing of these swimmers. So if Betty finishes first and Cam second and Deanna third, that is different than if we take those swimmers and we flip the order and maybe Deanna finishes first, Betty second, Cam third. So here the order does matter. And as we've learned, when order matters, we can deal with P's, or we can actually deal with the blanks. But P's are easier here. We have 5 swimmers in total. We're going to take 3 of them. Calculating that out gives us 60 total ways. In example B, now we're only qualifying for the next heat if just the top 3 move on. So now it doesn't matter if you finish first or second or third. You move on no matter what. So maybe somebody's not giving their full effort and they know they can get away with doing that, but the order doesn't matter. And as we've seen, this works with combinations with C's, so still 5 swimmers in total. We're going to see 3 of them. Calculate that out to 10 different ways. Moving on, we have a band recording 3 hit singles over its career. Not a bad career, but not a great one. One of which went platinum, and platinum is just a determination of how many copies it sold. So you can have hits, you can have gold, you can have platinum, you can have double platinum, and so on and so on. So the band members selected 15 songs, including those 3 hits, for the set list of tomorrow night's concert. So, does the order matter? Absolutely it does. I know myself, if I'm going to a concert and the first 2 songs are the ones that I want to hear, I legitimately will think about getting up and leaving. So they're going to want to sprinkle these out, maybe start off with one, then play some lesser known ones for a while, but the order does matter. So and how many set lists exist? Well, if we're playing 15 songs, then we need to play all of them in that concert. So we have a couple ways of looking at this. We could call this 15 factorial, since we have to find all the arrangements of all of those songs. We could also call it 15p15, 15 songs in total, taking all 15 of them. The order does matter. Those actually work out to the same answer. We could also have drawn out 15 blanks, filled in 15 options for the first song, 14 for the second, 13, 12, and so on and so on. They all work out the same way, and they are all a massive number, which does work out into scientific notation. Sometimes we deal with arrangements that are that huge, and we can't round these off because of the fact they're scientific notation. We need to keep every decimal place because technically they're not decimal places. It's just the shorthand for writing that out. So when I do that, 1.307674,368, and then in my graphing calculator, it says E12. Your handheld calculator, you might actually see it, but it is times 10 to the power of 12. C, now we've put a constriction on this. How many set lists exist in which the platinum song is played last? So we have locked this into place. No matter what, that song is getting played last. So really, now it's the other 14 songs that are getting arranged. which would be 14 factorial. Or 14p14, but we know that that 15th song is locked into place and it's not getting shuffled around. Take that in the calculator. It also gives me scientific notation, but this one, depending on your exact calculator, may not. If it doesn't, write the number as is. If it does, 8.7178292 times 10 to the 10. Question D now, how many set lists exist in which the hits are played first, last, and in the middle of the set? We have two things to deal with. These songs are now locked in place as the first song, the middle song, and the last song, but I haven't said which one gets played first, which one gets played second. So we actually have two different groupings of songs here. We have the hits, and we have the not-so-hits. So the not hits, those 12 other songs, we can arrange those 12 factorial ways. That's not a big deal. But those hits now, there are 3 of them, and I could play ABC, BCA, CAB. So I can actually, when I'm picking those hits, I can actually arrange those ones in 3 factorial ways around the not hits. So if I take that and I calculate it out, I get 2,874,009,600. Now, that may not be obvious to you why it works out that way, so this might be a case where using blanks is actually a better option. We have, I'm going to show it to you that way, it's going to work out the same. We have 15 songs, and what we know is that the hits are played first, last, and in the middle. So if we treat it this way, I have 3 different hits I can choose to play in the first spot in the concert, 2 to play in the middle spot, and 1 to play in the last spot, because obviously I'm not playing the same song twice. Then I have my 12 non-hit songs, which I can arrange however I want, but no matter what, I have 12 options for that spot in the concert. 11 here, 10, 9, 8, 7, 6 for the one after that hit, 5, 4, 3, 2, 1. Now this may not look like the same calculation, but if we look at the hits, 3 times 2 times 1, that is the same as the 3 factorial. If we take a look at the non-hits, 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is the same as 12 factorial. So the decision making here, which method to use, I chose the method that involved less writing. Maybe that works for you, maybe it doesn't. Maybe the method with more writing but a little more common sense works for you. Doesn't matter, they will work out to the same answer. It's just that method varies, even though they give us the same answer in the end. A piano teacher and her students having a group photo taken, 3 boys, 5 girls, along with the piano teacher. Photographer wants the boys to sit together and the girls to sit together for one of the poses. So in order for that to happen, we have 2 different groups we have to deal with. We've separated this out into the boys and the girls. So when we sit these people down, we could have all of the boys on the left sitting together. We could have all of the girls on the right sitting together. Or we could have the girls on the left and the boys on the right. So now looking at the boys, we have 3 of them. We're obviously going to put all of them into this photograph, and the order that they sit makes a difference. It matters, because Billy and Bobby do not look the same. So we have our 3 boys, and because the order matters, P3. Girls, same reasoning. 5 girls, and we're going to take all 5 of them. And exactly the same the other way, except in reverse. 5P5 for the girls, 3P3 for the boys. If we work out the math, this way works out to 720. This way also works out to 720. And because we're dealing with 2 sides of the same coin, 720 arrangement with boys on the left, 720 arrangements with girls on the left. To get the total number of arrangements, we'll add those together and get 1,440. One more example. How many different 5-colored poker hands can be dealt that contain at most 2 black cards? So now we've gone into the land of different cases, because in this situation, 2 black cards is okay, 1 is also okay, and none is also okay. Now, we can't deal with that all as one go. We need to deal with that in each separate case. So if we're looking at the case of getting 2 black cards, means we're going to get some black cards, we're going to get some red cards. The arrangement of the black cards, we have 26 blacks in a deck. When we're getting dealt a hand of cards, the order that we get them doesn't matter. So it'll be C, and we're getting 2 of them. The red cards, there's also 26 red cards in a deck. Again, the order that they come at us doesn't matter, so C. And in order to fill up that 5-colored hand, we'll need 3 red cards dealt to us. So we calculate that out, that should give us 845,000 different 2 black colored hands. And like I said, 2 black cards is acceptable here. Also, 1 black card is acceptable here. Same situation, we're going to have some black cards, we're going to have some red cards dealt to us. Still 26 black cards in a deck, but now we're only going to get 1 of them. Still 26 red cards in a deck, but now we're going to get 4 of those. Doing the math on this, we get 388,700. Last situation that's acceptable here, we could have no black cards. And in that case, we just get red cards. Still 26 red cards in a deck, but now we're going to get all 5 of the cards dealt to us as red. Work that out to 65,780. Now we know how many individual hands we can get. The total number that meet all of those conditions, we'll add those together. and end up with 1,299,480.